Hey guys, so this is going to be somewhere between 10-15 minutes, teaching a little bit about equilibrium reactions. The first thing you see here are graphs. And I know this is tough, right? So I'm going to go through all this again tomorrow, but I'm going to give you a worksheet with just a few, maybe like 5 questions that you can use this video to answer due tomorrow. We'll go over that tomorrow. Then I'll kind of reteach some of this stuff, and then we're going to go over some new stuff on Monday, and we'll take a few days to do this. So really, no worries if you're confused. But so I'll start here. So if you look at these graphs, and actually, let me first go to. So I'll come back to that. This. So what you can see here in a minute is when you have a reaction at equilibrium. So first of all, I guess I'll title this thing here equilibrium. And the term equilibrium does not mean equal by any stretch of the imagination. Equilibrium basically means a reversible, there we go, reaction that is constant, and I use the word balanced. Now, constant and balanced, I'm going to put in quotes because I use a seesaw as an analogy. I actually, in class, have a 2x4 with some wood, and I use different masses from Mr. McConnelly, and I move them around, and when the seesaw is balanced, that represents equilibrium. And I have a couple videos I'm going to show here to help teach that. And then tomorrow in class, or Google Meet, I kind of recreated that with a ruler and some money, like dimes, pennies, nickels. So we'll see how that goes. But anyways, essentially, if you have a reactant and it makes a product, well, sometimes that product can make a reactant. So when you see that double arrow, that means it means it's reversible, meaning it can go either direction. And if it's at equilibrium, what that really means, so what equilibrium really means is as one reacting, as one reactant, so let's say one particle, I should write one particle, as one reactant forms a product forms a reactant. We've already kind of learned this. All right, let's see if I can move this up here. We've already learned this when we talked about dynamic equilibrium. So if we have a beaker of water and we seal it, put a watch glass, let's say, on top, all right, this will reach what's called a dynamic equilibrium, where you have particles evaporating and then particles condensing at the same rate. So every time one of these liquid water particles evaporates out, you have a water vapor particle that might condense here, and it drips back in to the liquid. So that occurring at the same time, simultaneously, as one is evaporating and one is condensing, we call that equilibrium. We call it dynamic equilibrium because it's changing phases. So eventually, when you have a sealed container, you reach up here what's called equilibrium vapor pressure. So I'm not going to go into all that again, but I'm trying to refresh your memory that we have talked about that. So basically, if I can draw a picture here, all right, so let's say you have a reactant making a product. And by the way, and I'll kind of just do a dotted line here. You do not have to have the same number of particles on both sides. So, when you have balanced equations, sometimes you have big numbers 2 in front, and then over here you won't have a big 2. Yes, you have to have conservation of mass, but what I'm trying to start to lay the groundwork for here is, you can have, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 reacting particles, and you can have 1, 2, 3, 4, 5 products, right? So let me color match that. So if this reaction is at equilibrium, so we have an arrow going this way, if it's at equilibrium, what that really means is this ratio of reactants to products will never change. It is constant. Another analogy I use with this is a revolving door. So a revolving door at a hotel, right? So if you have a line of people outside, a line of people inside, you may have 100 people outside and you may have 50 people inside. Well, if one person walks in and one person walks out, you always have 150. It never changes. So that's what this means up here. As one reactant forms a product, the product forms a reactant. So let's say this particle comes over here, and now it turned into a product. Well, now it's gone, right? It's not here anymore. It turned into a product. Well, at the exact same time, let me fix that. Exact same time, one of these products came over here and now turned into a reactant. So basically what I just did there is if one of these dots comes over here and one of these dots comes over here at the exact same time, I always have 5 of these and I always have 10 of these. That will never change. So if I go back up to here, I said constant and balanced because that's exactly what this is. Assuming this is a balanced equation. I know I'm using R and P. I'm going to use real examples in a minute. But that's essentially what equilibrium is. All right. So that's it. If you don't learn anything else from watching the video, you just understand that equilibrium means reactions can go forward, they can go in reverse, and when they are at equilibrium, the amount or concentration of reactants and products stays constant. Why? Because every time one of these switches, or if 2 of these switch, then 2 of those switch. So they're constantly going back and forth, maintaining that equilibrium, which we say is constant, and I say balanced, kind of like a seesaw. Okay. So again, the analogy here would be, I'll use a different color here. Let's say the seesaw underneath it here, right? So you got your reactants here, and you got your product here. Yes, there's a 2 there. That is irrelevant. It doesn't mean anything. It means 2 moles of reactants produce 1 mole of products. And in this case, it's balanced. So if this is a seesaw, this side is balanced with this side. The seesaw is level. It isn't tipped to one side or another. Once we start getting into tipping that seesaw, right? So the reactants down here, products up there, reactants up here, product. Once we start getting into this, that is the next phase here. That's called LeChatelier's principle. How does this equilibrium, how does this reaction, how does this seesaw change to go back to being balanced? So I'm going to stop with this here. This is pretty good as far as keeping it simple here. Now I'm going to introduce LeChatelier's principle. I'm going to talk about temperature and concentration. And, for the sake of time, I think I'm already, let me see where I'm at here. Yeah, so I think for the sake of time, I'm not actually going to show you any videos. I'll do all that tomorrow or Monday. I'm just going to stick with this whiteboard here. So I'm actually going to get a new whiteboard because I think I can refer to this tomorrow. So let's see. How do I do this? There we go. Okay. All right. So here we go. All right. So LeChatelier's principle. LeChatelier's principle. All right. What does that mean? It means when a stress is applied to a system at equilibrium, the system changes or adapts to reach equilibrium. Actually, you know what? Let me rephrase that. I have a better way to say that. The system changes or adapts to maintain. That's a better word. Maintain equilibrium. And the stresses are temperature, concentration, and pressure. So sorry this is messy, but what else is new, right? So that's supposed to be an R there. All right, temperature, concentration, pressure. So when a stress is applied to a system at equilibrium, system changes or adapts to maintain equilibrium. You know, not to get all philosophical here, but that's like life, right? When stress is applied to us, whether it's our doing or not, right? Sometimes things just happen and create stress for us. When stress is applied to our lives or situations, most of us want to deal with it, alleviate it, do whatever we need to do to fix it, to get back to not having that stressor. And that's my analogy there with equilibrium is, let's say you're at equilibrium. Life's pretty good. Don't have a lot of stress going on. Something pops in your life. There is a lot of stress. You do what you can. You deal with it. You change. You adapt so that you can go back to being happy, right? Balanced at equilibrium, right? So that's the same thing here. So that's LeChatelier's principle definition. Kids don't really learn too well from definitions. Some do, but better are examples and labs and stuff like that. So let's just do a simple example here. All right, I'll give you a real reaction. Let's go with 2H2 plus O2 equilibrium 2H2O. All right, and now the value of delta H here, let's see if we can look this up. All right. Got to go to table I. Sorry, I should have had this set up to save some time. Where are we? Right here. Let's do the gas. Negative 483.6. Negative 483.6. So 483.6. All right. Kilojoules. All right. So here's the first thing we'll do with concentration. So here's a concentration example. If some O2 is added to this reaction, in what direction will the equilibrium shift? And what this basically means, all right, let me move this up a little bit here, get that out of the way. Okay, here we go. All right, so this is a concentration problem. This is LeChatelier explained how temperature, concentration changes, and temperature affect equilibrium. And I think I might just stick with concentration today because I don't want to make this video too long. So your homework's going to be very short, but I'll give you just something to get the ball rolling for tomorrow. All right, so if I add more H2, if I add more O2, if I add more H2O, or if I take some away, that's decreasing or increasing the amount, concentration. This question says if some O2 right here is added, so we start dumping O2 into this reaction, the equilibrium won't be balanced anymore, won't be at equilibrium. So it'll have to shift. And shifting means we're going to make more products or make more reactants. So I use the analogy of a seesaw. So here we go. So if we have a seesaw, and here's my 2H2 and my O2, here's the arrows, and here's my 2H2O. All right, well, if I start dumping more O2 here, so if I add more O2 to this side, imagine it's a seesaw. What's going to happen is this side's going to get heavier. So now my seesaw looks like this. Here's my 2H2O up here. I have my O2 and my 2H2O down here. All right, why? Because we just dumped a whole bunch of O2, right? So we have those 3 O2. So now this side's too heavy. I use the word heavy in quotes. It isn't about mass, but you can understand this. So now we added O2. What does that mean? We increased the concentration. There's more O2 than when we started. When we started, it was balanced. Once we added more O2, we increased that concentration. It's no longer at equilibrium. The analogy is when it's balanced, it's at equilibrium. So what has to happen? So basically, the way these reactions work is if you add reactants to alleviate the extra reactants, they react. And what do? They form products. So some of these are going to react, make more water, and they'll make just enough to go back to being balanced. So now if this is picture number 1, picture number 2, I'll do number 3 over here. So now we're back to being balanced, 2H2O, O2, 2H2, 2H2. So basically, the way these questions work is they're going to give you some kind of change in concentration. They're going to say, let's add more, let's take some away. Well, let's say we add some more reactants. So if you add more reactants, you have to think of it like a seesaw. It's going to go down, right? It's going to be heavy. It's going to hit the ground. H2O is going to go up in the air. Well, the only way in this analogy to get it back to being balanced is if some of the reactants come over here and come on the product side. Well, remember, it's a chemical reaction, so it's not like they're just walking here, right? Like people could just get up off the seesaw and kind of walk over here. That doesn't work. So what has to happen is they actually collide, effective collisions, make a product, and make more water. When they do that, this side slowly starts to come up, and this side slowly starts to go down, and eventually they will be back at equilibrium. And it will be happy, constant, balanced, all of those terms. So the answer to this question is right here. So you dump the O2 on the left side. Which way does it shift? Which direction? And the answer is going to be left or right, towards products, towards reactants. So in this case, these reactants have to go to the product side. They have to react and make more products. So we are shifting to the right. The answer to this question is shifting to the right. Some of the reactants must react and move, essentially move to the product side, make more products. Now we are back to being balanced. So the answer to this question is it shifts right, or we could say shifts towards products. Shifts right or shifts towards products. So my video is already longer than I wanted it to be, so I'll probably just stop here. Let me see. Yeah, 17 minutes. Yeah, that's too long. So I'm going to stop, and I will teach more about this tomorrow. So those of you who watch this, I appreciate it, and at least it helps you start to understand what we're doing here. All right, I will see you guys tomorrow.